Hello everyone, we have a problem here that says a laser light beam has a wavelength of 500 nanometer in vacuum. If the beam is traveling in vacuum, evaluate the corresponding values of the wave vector k. And here we just want the magnitude of k and the angular frequency omega. Okay, so we're given lambda in vacuum, and that is 500 nanometer. And we know that k, the wave vector, or at least the magnitude of k here, which is what we want, is equal to 2 pi over lambda. So 2 pi over 500 times 10 power minus 9, just to convert this to meters. And we would get, I'm going to keep everything in terms of 2 pi. So we're going to have 2 pi times 2 times 10 power 6. And that's going to be meter minus 1 or 1 over m. And that's the wave vector, the magnitude of the wave vector k. Okay, now we need the angular frequency omega. There are multiple ways to do this. One way would be, we know that omega is equal to 2 pi frequency, which is the same as 2 pi over t, the period. Do we have the frequency? Well, it's not given to us directly, but we know that it's traveling in vacuum, right? And it's light. The speed of light in vacuum is c, which is approximately 3 times 10 power 8 meter per second. And we know that c is equal to lambda f, where lambda is the wavelength and f is the frequency. If you find this confusing, an easy way to think about it would be, we know that speed is equal to distance over time. Distance here is the wavelength. It's how far the signal will travel. That's the wavelength, right? So that's lambda. And you divide by the time it takes to travel that distance, t. And we know that f is 1 over t, so c is equal lambda f. Anyway, back to our question. So c equals lambda f. We're given lambda. We know what c is. We can calculate f. So f is going to be c over lambda. So 3 times 10 power 8 meter per second over 500 times 10 power minus 9 meters. And we get 6 times 10 power 14 hertz. All right, so now we can calculate omega, which is going to be 2 pi times f, which is 6 times 10 power 14, and all is going to be rad per second, radians per second. All right, I like to keep everything in terms of 2 pi here. What's another way to calculate omega? If you don't want to go through calculating the frequency, then we know that the phase velocity, which is c here, is equal to omega over the wave vector, or the magnitude of the wave vector k, right? We know c, and we just calculated k above, so we can calculate omega, which is going to be ck, basically. So we have 3 times 10 power 8 meter per second, and we just calculated, let's just move this a little bit, and we just calculated k here to be 2 pi times 2 times 10 power 6 meter minus 1. All right, 3 times, I'm going to keep everything in terms of 2 pi. And then 3 times 2 is 6 times 10. 8 and 6 is 14, power 14 radians per seconds. And if you look closely here, this value for omega is the same as this value. So in this problem, we were able to calculate the wave vector magnitude of k and the angular frequency omega in vacuum. Now, assuming that this laser light is traveling through a medium that has a certain index of refraction n, and it's not traveling through vacuum, how would this problem change? Let's look at that. This is actually the second problem we have here, which is the same kind of question with the same wavelengths, 500 nanometer in vacuum, except that the beam now is traveling through a material and it has an index of refraction of 1.5. So n equals 1.5 of that material. Okay, and we need to find the magnitude of the wave vector, k, again, and the angular frequency, omega. Okay, we know that k, or at least the magnitude of k, is 2 pi divided by lambda, all right? But this lambda is the lambda of this material. I'm going to call it lambda n. The one that's given to you in the problem is lambda of the wavelength of this light in vacuum. Okay, and it's not the same. The wavelengths will change depending on the index of refraction of the material in which it's traveling. How much does it change? Well, that can be a bit confusing, so let's look at this. We know that c equals lambda f, the wavelength times the frequency. If you're having a hard time remembering this, an easy way to think about it would be c, which is the velocity, speed of light, is equal to the wavelength, omega, which is a distance, divided by time, which is a period. So assuming that we have, now this is just a very simple abstraction. This is a wavelength, right, lambda, and we're dividing by the time it takes to travel this distance, which is a definition of velocity. And we know that 1 over t, 1 over the period, is a frequency. So c equals lambda f. Right, anyway, back to our question here. Let's take f to be equal c over lambda. Now, the frequency of light, or the frequency of this certain light, will not really change when it changes mediums. If we're dealing with linear crystals and linear optics. So if we have two materials, one with index of refraction of n1 and the second has an index of refraction of n2, and we have a laser beam or some light traveling through them, the frequency will be the same. It's not going to change. But we know that the speed will change. The speed here will be c divided by n1. It will decrease by a factor of the index of refraction, and here will be c divided by n2. Of course, if we're traveling in air, then n1 is roughly 1, and c is just c. So c will decrease by a factor of n. Lambda will have to decrease by a factor of n. So now lambda sub n, the new lambda, is going to be lambda from vacuum divided by n. So lambda in vacuum is 500 nanometer divided by 1.5, which will roughly be 333.3 nanometers. Okay, now we can use this lambda to calculate the wave vector k, which is 2 pi divided by 333.3 times 10 power minus 9. I like to keep everything in terms of 2 pi, and this gives us 3 times 10 power 6. This is meters, so this is going to be meters minus 1, power minus 1, or 1 over m. All right. We also need to calculate omega. And we can do it in two different ways like we did in the previous problem. But in this case, I'm just going to do the second way, in which we said omega will equal the phase velocity times k, which we just calculated, right? The phase velocity is going to be c, the speed of light, divided by the index of refraction in which, this is in vacuum, right? Speed of light in vacuum, divided by the index of refraction in which the light is traveling, which is n here, multiplied times k. So we're going to have 3 times 10 power 8 meter per second divided by 1.5 multiplied times this k here, 2 pi times 3 times 10 power 6 meter minus 1, which should give us, I like to keep everything in terms of 2 pi, and this will give us 6 times 10 power 14 radians per second, which is the same value we got in the previous problem. And why is that? Well, because omega is equal to 2 pi f. Really, the only thing here that could change is f, but f is not going to change when traveling in linear optics between two index of refractions. We just discussed that. So we're expecting omega here to be the same as omega we calculated in vacuum, which checks. So this is correct. Thank you for watching. Let me know if you have any questions in the comments below.